let's take a look at an introduction to astrophysics and stellar quantities. So if we're going to study astrophysics, which is the study of the physics of things outside of the Earth and the Earth's place within all of that, then it makes sense to kind of stay close to home at first. So we're going to start here. Here's the Earth. The Earth is orbited by the Moon, which is quite a bit smaller than the Earth. A moon is just a smaller mass that orbits a planet. And what's a planet? Okay, well, a planet is a moderately massive object that orbits a star, in our case the Sun, in a roughly circular orbit that is clear of debris. So the Earth orbits in a roughly circular path around the Sun, and that path is not full of stuff. It's clear of debris. There are 8 planets orbiting the Sun. There's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And that's in order from innermost planet to outermost planet. The inner 4 planets are rocky. They are smaller. They don't have a lot of moons. Earth has 1 moon, Mars has 2, Mercury and Venus have no moons. The outer 4 planets are gas giants. They're much bigger. So Jupiter, Saturn, Uranus, and Neptune, pretty big planets, and they have many, many moons. Now, other objects within the solar system are asteroids. Asteroids are smaller, rocky objects that travel in usually elliptical orbits. Many of them are found between the orbits of Mars and Jupiter, but sometimes they stray. Out beyond the orbit of Neptune, there are Kuiper Belt objects. These are small planet-like things, but they're also kind of like big asteroids with a lot of ice. These are things like Pluto, and there's other ones called Eris and Makemake. And if you go out beyond these Kuiper Belt objects, there's the Oort cloud. The Oort cloud is made up of small, icy, dusty objects out there. And when one of these small, icy, dusty objects falls in towards the center of the solar system, that's what we see as a comet. So essentially the Oort cloud is a big comet factory out in the outer solar system. Now, when we deal with the solar system, it is often awkward to deal with normal units like meters. For instance, the distance between the Sun and the Earth is 1.50 times 10 to the 11 meters. It's kind of cumbersome to use those big numbers. So what solar system scientists often do is they use something called an astronomical unit, an AU. The AU is defined as the mean distance between the Earth and the Sun. So, like I said before, that distance is 1.50 times 10 to the 11 meters. This is given in your data booklet. If we do that, then Jupiter's orbital radius around the Sun is 5.2 AU. Pluto's orbital radius is, on average, is 39 AU. And then this Oort cloud, the outer part of the solar system, that's 2,000 to 100,000 AU from the Sun. Now, that might sound like it's pretty far away, but the stars, the other stars, are much, much farther away. The nearest star is called Proxima Centauri, and it is 269,000 AU away. So, when we move beyond the solar system and talk about stars, the AU is also not big enough. It becomes cumbersome. So they start talking about things called light years. Proxima Centauri is 4.25 light years away. A light year is the distance that it's traveled by light in vacuum in 1 year. 1 light year is 9.46 times 10 to the 15 meters. That's also in your data booklet. The brightest star in our night sky is Sirius. That is 8.61 light years away. Polaris, the North Star, that is 323 light years away. Deneb, a bright star that you can often see in the northern hemisphere, is 2,620 light years away. All of the stars that we can see out in the night sky from Earth, they are in a group of stars called a galaxy. And the galaxy that we are inside of is called the Milky Way. The Milky Way contains about 100 billion stars. We cannot see all of them from the Earth, but studies have shown that the Milky Way contains about 100 billion stars. It's a disk. It's shaped like a big disk that's 100,000 light years across and about 1,000 light years thick. And then it's got a bulge towards the center. So it looks a little bit like this. It also has spiral arms. Milky Way is what's called a spiral galaxy. Now, there are other galaxies out there. The nearest neighboring major galaxy is Andromeda, and that's 2.5 times 10 to the 6 light years away, 2.5 million light years away. And that galaxy contains also hundreds of billions of stars. There are hundreds of billions of galaxies, and each galaxy contains hundreds of billions of stars. So the universe is absolutely huge, and it's kind of hard to conceive of just how much there is out there. There are other structures out in space that you should be aware of. One is binaries. Binaries are pairs of stars that orbit each other. So our sun is a star by itself. It does have planets and other stuff around it, but there's no other star in our solar system. Most stars come in pairs, called binaries. In fact, the nearest star system to us is a trinary. It's 3 stars that orbit each other. Out around other stars, there are often other planets called exoplanets, planets that orbit other stars. And over the past 15 years, we've discovered more and more and more of these. Out there's also things called nebulae. Nebulae are clouds of gas that are absolutely huge and absolutely massive, although the mass is spread out over a very large volume. And these are the clouds from which stars are born. In some cases, the clouds, or part of the cloud, can start to collapse and form a solar system. These are found within galaxies. So the spiral arms of the Milky Way, our galaxy, are largely made of these clouds of gas. Out there's also things called open clusters. These are loose groups of stars that travel together and were probably born together and are kind of a group that travel along. There's also globular clusters. These are much more dense groups of stars that travel together, and they're often seen just outside of galaxies. So for example, in the Milky Way, just outside of that big disk making up the Milky Way, there's globular clusters all over the place. On the galactic scale, there are clusters of galaxies. So galaxies come in these cluster structures where the galaxies kind of orbit each other and are locked in a dance together. And then beyond the clusters, there are superclusters of galaxies, which are like clusters of galaxies. And these superclusters of galaxies are the largest structures in the universe. Now, if you've ever looked up at the night sky and it's been dark enough for you to see a lot of stars, you've probably noticed patterns of stars up there. People have noticed this a very long time ago, and they developed these things called constellations. Constellations are just patterns of stars that we can see here from Earth. So, for example, Orion. Someone a long time ago looked up, saw some stars, thought it looked like Orion the Hunter. Another group of stars, they looked up at it and they thought it looked like a Big Dipper. Another group, they looked at it and thought it looked like a swan, so they named it Cygnus. So these constellations are groups of stars that reminded somebody of something a long time ago. And it's important to notice that constellations are only visible from the Earth. The patterns that we see from Earth are not patterns that are actually out in space. The stars within the Big Dipper are not actually close to each other. And the stars within Orion are not close to each other. So they're not like open clusters and globular clusters where the stars are actually physically grouped together out in space. Constellations are groups that show up in our night sky, even though the stars themselves are not actually close to each other in reality. All right, so let's go back to stars themselves, and we'll use those as kind of a foothold for astrophysics in general because they're what we can easily observe in the night sky. You look up, you see stars. So what are they? Okay, well, stars are huge balls of hot gas. Sort of. They're not really gas. They're another phase of matter called plasma, which is very, very hot gas that is so hot that some or all of the electrons have been ripped off of the nuclei. Stars are mainly made out of hydrogen. You might ask why. Well, the reason why stars are mainly made out of hydrogen is because the universe is mainly made out of hydrogen. At least the normal matter that we can see is mainly made out of hydrogen. And if you ask why is it mainly made out of hydrogen, well, because the universe started out with a big soup of protons and electrons, and the simplest thing that those protons and electrons could form was hydrogen. which is just a single proton and a single electron. So, okay, star, big ball of hot hydrogen. And when I say big, I mean really, really big. The masses of stars go from about 10 to the 29 kilograms to 10 to the 30. Now, the deeper you go in this huge ball of mass, the more mass is pressing down on the star at that point. So deep in the star, there's a huge amount of force downward from the mass that's above it. There's a greater inward gravitational force the deeper you go. So at the center, in normal stars, the pressure is great enough to actually fuse hydrogen nuclei together. This fusion of hydrogen, we've seen, releases energy. Fusion is the energy source of a normal star. And note that this fusion only happens at the center of a normal star. In the outer part of a star, the pressure is not great enough to cause the hydrogen nuclei to fuse. It's only at the core of the star that it's great enough. The temperature inside the star is enormous. So there's an enormous gas pressure also. And this outward gas pressure is great enough to oppose the equally enormous inward gravitational force. So this balance, this so-called hydrostatic equilibrium, is the balance between an inward gravitational force from the large amount of mass that's attracting and the outward gas pressure that's pushing outward from the center of the star. So that's what stars are, but how the heck do we know anything about stars anyway? Like, how do we even know how far away they are? Well, the most direct way to get the distance to a star is with something called stellar parallax. It's a geometric method, and I'm going to draw a picture to show you how it's done. So here's the sun, and here's the orbit of the Earth around the sun. And let's say there's a nearby star right here, and then there's very distant stars that are way over there. So let's say an astronomer measures or observes this nearby star when the Earth is right here. And then the astronomer waits 6 months and looks at the same star again. Well, initially, the star appeared to be here against the backdrop of stars. 6 months later, when you look at the star, it appears to be here against the backdrop of stars. So the nearby star seems to move against the backdrop of stars. The angle right here is called a parallax angle, and astronomers can observe this angle and use it to find the distance. Because if you look, there's a big triangle right here. And if you know this angle, and you know the length of this side, you can figure out the distance to the star. This is a very important method, and it's an important enough method that a distance unit is actually defined using this. So I'm going to write down an equation that comes from this method. D is equal to 1 over p, where d is the distance to the star, and p is the parallax angle. Now, this only works if you use certain units. P, the parallax angle, has to be measured in arc seconds. Well, what's an arc second? An arc second is 1/3600th of a degree. It's a very small angle measurement. And if the parallax angle is measured in arc seconds in this equation, then the distance will be given in a unit called a parsec. A parsec is the distance at which the parallax angle is 1 arc second. And a parsec, it turns out, is equal to 3.26 light years. And the parsec name actually comes from the first 3 letters of parallax and the last 3 letters of arc second. So parsec. Now, the parallax angle is really tiny, and it's difficult to measure. So for the nearest star, Proxima Centauri is 4.26 light years away. That's 1.3 parsecs. So the parallax angle to the nearest star is 0.769 arc seconds. The nearest star has that small of a parallax angle. Parallax angles are tiny, and they're very difficult to measure, especially from Earth. On Earth, they're only observable, like they can only be measured for stars that are out to about 100 parsecs, or 326 light years. Beyond that, the parallax angle is too small for Earthbound astronomers to measure. Satellites can do better. So outside the distortion effects of the atmosphere, satellites can measure parallax angles down to about 10 micro arc seconds. So they can measure distances to stars using this parallax method out to about 100,000 parsecs, or 326,000 light years. All right, so now let's think about the light that we get from stars. And the reason why the light that we get from stars is so important is because that's really all we get. When you look at a star, all you get is the light. So first thing we're going to define is luminosity. Luminosity is the total power emitted by a star, or any other object, but here we're going to talk about stars. So the sun's luminosity, or the amount of power that it emits, is 3.83 times 10 to the 26 watts. It's a lot, but that makes sense. It's the sun. It gives off a lot of power. Another star, a very large star called Eta Carinae, has a luminosity of about 1 times 10 to the 33 watts. So that's a few million times larger than the sun's. Some small stars have luminosities of about 10 to the 23 watts, or about 1,000th of the sun's. And the luminosity of a star is equal to sigma A T to the 4th, which probably looks familiar. This is from the black body equation. Stars can be approximated as black bodies, with an emissivity of approximately 1. It's not entirely true. They're not perfect black bodies, but it's an okay approximation. Now, the brightness of a star is different. The brightness of a star is the power that is received from a star per square meter by an observer on the Earth. So if we think about it, the brightness is equal to luminosity divided by 4 pi d squared. And the way to think about this is the luminosity that's coming out of a sun, the total power emitted by the sun, is spread out over an entire area, the surface of a sphere. Imagine a sphere surrounding a star. That energy is distributed around that entire area. And the area of that sphere, or the surface of that sphere, is 4 pi d squared, if the distance to that sphere is d. So the brightness of Sirius, for example, which is the brightest star in the night sky other than the sun, is about 10 to the minus 7 watts per square meter. So that's telling us that from Sirius, brightest star in this night sky, we receive 10 to the minus 7 watts per square meter here on Earth. Now the brightness of the sun is the solar constant, right? Because the brightness is the power that's received per square meter. Well, the power received per square meter from the sun is the solar constant, 1,360 watts per square meter. So I want to point out this brightness is equal to luminosity over 4 pi d squared. If you look, distance shows up in that equation. So brightness is something that we can measure from the Earth. We look up at a star, we can measure the amount of power we receive per square meter from that star. If we had a way to determine the star's luminosity, well, we can measure the brightness. If we knew its luminosity, then we could use this equation to get the distance. And we'll discuss that next time, ways to get the luminosity, because if you know the luminosity and the brightness, then you can get the distance to a star.